And welcome everybody to today's webinar on non-convex quadratic optimization in Gurobi 9.0. So first, let me introduce what mixed integer quadratically constrained programming is. So an MIQCP is defined as this mathematical program that you can see here on the slide. It is similar to a mixed integer linear program, except that the objective function and also the constraints may have some quadratic terms in them. So these Q matrices that you see here in the model, they should of course be symmetric. And for any non-zero element in such a Q matrix, Qij not equal 0, this gives rise to one product term in the constraint or in the objective. Now, if all of those QK matrices are positive semi-definite, then the QCP relaxation, that means just ignoring the interquadratic constraints, is convex. So in those MIQCPs with positive semi-definite QK matrices can be solved by Gurobi since version 5. But now the question is, what if those quadratic constraints or objectives are non-convex? So there are a large class of applications for those non-convex quadratic programs, in particular if the constraints are non-convex. One of the most important one is the pooling problem, which appears in the petrochemical industry, but there are also a number of other industries where such problems arise. You can see those here on the list. I won't go through them here. And then, of course, at least in theory, you could also think about general MINLP problems, so with nonlinear constraints, not necessarily quadratic. So those can be approximated by polynomials. So, and if you have a non-convex MIQCP solver, then at least in theory, you could solve any polynomial problem of arbitrary degree. And by approximating MINLPs as polynomial problems, you can then approximately solve general MINLPs. But of course, this will usually fail in practice, in particular for higher degree polynomials, because you get severe numerical issues in the solution process. But anyway, regular non-convex MIQCPs are already useful in practice on their own. So let's see what Gurobi 9.0 does to solve them. So if you look at prior Gurobi versions, then those Gurobi versions can solve quadratic problems as long as the Q matrices are convex, or at least if after pre-solve has been applied, they have been turned into convex constraints or objectives. So what does it mean to be convex? So one condition for convexity is that Q is positive semi-definite, or to say it more precisely, if the matrix is positive semi-definite, then the corresponding constraint x transpose Qx smaller or equal to b is convex. But there are also convex constraints where the Q matrix is not PSD. So one very important example is given by the second order cones. You see here a second order cone in standard form is a sum of squares, and then there is one square variable that has a -1 coefficient. This is the cone top variable here, which is in this case z. And yes, you can see here in this picture, this object that is defined by this constraint is this cone here. And the important part is that the z variable is non-negative, because if the z variable could be negative, then the corresponding object would be such a double cone, and this would no longer be convex. But if the z variable is non-negative, this gives a convex object, and this Gurobi can deal with also in earlier versions than Gurobi 9.0. Okay, but Gurobi 9.0 now can deal with this other type of quadratic constraints, the non-convex part. So older Gurobi versions have already been able to deal with non-convexities, of course. The primary example here is integer variables. Those make the problem certainly non-convex. And there is a second class of objects which we have been able to deal with, which are SOS constraints. But now Gurobi 9.0 introduces a third type of non-convexity in their solving algorithms, which are the bilinear constraints. So bilinear constraints are a special type of non-convex quadratic constraints. We'll see this in the following. And similar to integer variables and SOS constraints, we deal with these bilinear constraints through cutting planes and through branching. But in order to be able to solve a general non-convex quadratic program, we first have to convert those non-convex quadratic terms into bilinear constraints, such that then our algorithm that can only deal with bilinear constraints can work on those. Okay, let's see how this is done in Gurobi, in this Gurobi 9.0 version. As an example here, we start with this quadratic equality constraints. So quadratic equality constraints are always non-convex. And here we would take each product term and introduce an auxiliary variable to represent this product term. So for example, x1 square is then represented by this new variable z11. And x1 times x2 is represented by this new variable z12, and so forth. So this gives us, for this constraint, 6 additional variables that are linked by 6 bilinear constraints to the corresponding product terms. And then by substituting these new variables for those product terms, the original non-convex quadratic constraint becomes a linear constraint. So that means we now have only linear constraints and bilinear constraints. And this is what we wanted. And now I only need to explain to you what we do in order to deal with those bilinear constraints. Okay, so some more details on the bilinear transformation, because that is not so trivial what you want to do. There are other options, and it's not clear which of those options give the best performance. So this is our approach that I just told you, just to say it in a bit more details. So we look at each term xi times xj individually in such a non-convex quadratic constraint, and now check what is going on with those variables. So first, the easy case is that one of the two variables, or even both of the two variables, are actually fixed. In this case, this is not a product term, but it is actually a linear term or even a constant, and that can be moved to the right-hand side of the constraint or to the linear part of the constraint. So that is easy. But now it can happen that we have a square term, so I is equal to j. So we have aij is times xi square, and the xi variable is binary. Then this is also very simple, because for binary variables, it is true that xi square is equal to xi, and that means the term is again linear and can be moved to the linear part of the constraint. Now another case appears if those two variables are different variables, but still one of them is binary, or both of them are binary. Then we can always convert this particular product term into a linear term by adding the appropriate linear representation of the product. So if the bounds of the other variable, so the non-binary variable, are small enough, then we can use a big M linearization to represent the Zij variable. And if the bounds are too big or even infinite, then you can use an SOS1 formulation for this product. So again, this makes it linear without having to introduce bilinear constraints. And then there's another case, namely that we have two different variables, so really a product of xj, I times xj, and the coefficient in front of the product is positive, and the constraint is a smaller or equal inequality. In this case, we can keep the term in the quadratic part, because then the resulting thing, of course, it's no longer linear, but it is quadratic, but this will then be convex. Okay, and finally, if all of this is not true, then we have to introduce this auxiliary Zij variable plus the bilinear constraint to link it to the xi times xj product. And so we have the bilinear constraints that I've been showing you in the previous slides. Note again that those bilinear constraints not necessarily have to be equations. They can also be inequalities depending on the sign of the a coefficient and whether the original quadratic constraint is an inequality or an equation. Okay, this is how we do it. It's also possible to use more sophisticated partitions into convex and non-convex parts that give better relaxations. This is something that we have not yet explored and may want to do this in the next version. Okay, I want to point out that these particular cases that you see here highlighted, those are optional, so you don't need to do them. But my hope was, when I implemented this, that they give better performance if we actually do this. So this trick with the binary variables to linearize them, and the trick of keeping the positive square terms in the formulation because they stay convex. So then I ran a performance run on our test set to see whether these two ingredients really help performance, and this is what comes out of it. So you see here our test set has 444 models. Some of them get discarded due to numerical issues. Some of them get discarded because none of the 3 versions that I consider here were able to solve them. And then we look at the speed up on the what we call the larger 10-second bracket. These are all the models where at least one of these 3 versions in this case consumed at least 10 seconds to solve them. So those are the not so easy models, I would say. Okay, and then we take the geometric mean over all of those problem solves and divide this by the default solve time geometric mean. So the default, which is our current Gurobi 9.0 version, will always have a value of 1.0 here because that is what we compare to. And now if the value that you see here for the other two is larger than 1.0, it means that the other solver in this case is slower than the default. So what you see here in the slide is what I expected for the binary linearization. If I disable the trick with treating binary variables, then indeed we get an 11% performance degradation. But then the other bar shows something that was surprising to me, namely when I disable the trick with keeping the positive square terms. So I would also linearize those terms, even though I do not have to. Then the resulting solver is actually 6% faster than Gurobi 9.0 on this test set. So this is something that we need to explore in the future a little bit more. So my speculation is what happens here is by also introducing bilinear constraints for those positive square terms, we get some additional monomial variables, so these Zij variables, and they will later help to be able to find better cutting planes. So that's my speculation. Okay, now we have this transformation into bilinear constraints. Now I want to show you what we need to do in order to deal with them on an algorithmic level. So in general, our bilinear constraints have this more general form of a regular linear term A transpose Z. So A is here now a vector and Z is a vector of variables, and a single product term with a coefficient D in front of it. So D xy, and that can be small or equal to b or equal to b. So that is our general bilinear constraint. And now let's first consider the square case. So actually we have x is the same variable as y, and in this case we can look at the coefficient of the z variable and see whether this constraint is convex or not. Sorry, the coefficient of this x square term. So if in this particular case we have minus z plus x squared smaller or equal to 0, then we are convex, and if the coefficient before the x squared is negative, then we are non-convex. So let's consider these two cases. So the convex case, that is really easy to deal with. This is something that Gurobi 8.0 and prior versions have already been able to deal with. Namely, we can just add tangent cuts. So we start with some linear programming relaxation, and this green dot here should be an optimal solution to this linear programming relaxation. This is of course not feasible because it is not inside the feasible blue region that you see here. But now we can just separate a tangent cut to cut it off, and then we go somewhere else in this LP polyhedron. This might be this corner point here, and then we continue adding tangent cuts until the solution is close enough to the feasible region within the feasibility tolerance, say, and then we stop adding those tangent cuts, and that's it. So for the non-convex part, it's much harder because often the LP relaxation optimum solution will be somewhere here in the middle. And the problem is we can't get a better linear program relaxation because any hyperplane that would be better than this that you see here would also cut off a certain part of the feasible region of our constraint. So similarly, we can also not find any cutting planes here to cut this point off. So this point could be there in this middle. This could be an LP vertex solution because of other constraints in the problem that you don't see here. And now what can we do? The only thing that we can potentially do is to branch. So we would split this variable into two parts. And now, since now the two feasible regions in the two child nodes are smaller, we can tighten the LP relaxation of this feasible region. And in both child nodes, we would cut off the feasible LP solutions from the parent node. So this is how it works, branching on this continuous variable. So that is called spatial branching. Okay, now let's look at the regular case of two different variables being in the product. So here the LP relaxation, of course, needs to be three-dimensional in this pictures. And you see here the so-called McCormick envelope. So this is the convex hull of this saddle type shape. And the two first constraints that you see here, those are the lower envelope constraints, and the other two constraints are the upper envelope constraints, and they form this polyhedron that you can combine from these two things that you see on these pictures. Now, the most important point here is that these coefficients of these McCormick constraints depend on the bounds of the variables, in particular on the local bounds, so the bounds that are valid locally in this current subtree. That means those coefficients and right-hand sides of those constraints will change all the time during our solving algorithm. Whenever we go into some local search tree node, the bounds will change, and thus the coefficients and right-hand sides of those constraints will change. And this leads us to the concept of what we call adaptive constraints in the LP relaxation. So as I said, the coefficients and right-hand sides of the McCormick constraints depend on the local bounds of the variables. And that means whenever the local bounds change, because we switch to a different node in the search tree, the LP coefficients and right-hand sides need to be updated. And if you know how MIP solvers work, they take the current LP basis of the parent node and use this as a warm start for the child node LP solve. But if the child node suddenly has different coefficients and different right-hand sides in the LP relaxation, it could actually be that this particular warm start basis of the parent node is no longer a basis because it becomes singular. And then the simplex algorithm cannot continue. It can try to get around by some numerical tricks, but in the worst case, it may even need to start from scratch. So this might be very costly here if we have many such situations where we need to start from scratch. But of course, the hope is that this will not happen too often. But there would be an alternative to avoid this, which is to not use our concept of adaptive constraints, but instead add those tighter McCormick constraints as locally valid cuts. So the tighter McCormick relaxation would then be added on top of the weaker, more global one to a local node's LP relaxation. Here, the advantage, as I said, is that the old simplex basis will always stay valid. And then if you solve the child node, then most likely the more global McCormick constraint will become slack and get into the basis, while the tighter local one will become non-basic and thus tight. And this should lead in average to fewer simplex iterations. The disadvantage of this local cut approach is that the basis size, so the number of rows in the LP relaxation, will change all the time during the solve. So whenever we switch to a different node in the search tree, the size of the basis will be different. And that means in particular that we have to refactorize the matrix all the time. So whenever the basis changes, we have to refactorize. So this is costly, expensive. And it is also very complicated to have the data structures in place that support this always changing of basis sizes and so forth. And moreover, then if you do this and dive very deeply, then you will accumulate a large number of McCormick constraints that are no longer be useful because they are valid for a more global node and are dominated by the more local version of this McCormick constraint. But still, the LP solver would need to perform those useless calculations in order to calculate the slack values for these McCormick constraints. So overall, I think, but I've never tried it, that the adaptive constraint idea should be a little bit better than the locally valid cut idea. Okay, let's come to branching. So branching variable selection is always a very important topic in MIP solving. It doesn't matter whether it's MILP or MIQP or non-convex MIQCP in this case. The question is, which variable should we branch on? And now what we do is what most other non-convex MIQCP solvers and more general MINLP solvers do. First, we branch on integer variables that have fractional solutions in the current LP solution. So just the regular MILP branching strategies. But then if there is no fractional integer variable, then we have to select a continuous variable in some violated bilinear constraint. And here, our variable selection rule is a combination of trying to pick a variable where the sum of the absolute violations of bilinear constraints that this variable appears in is as large as possible, while on the other hand, we want to reduce the volume, so the geometric volume that you can see in the McCormick polytopes as much as possible, right? By splitting a domain of a variable into two parts, the volume of this polyhedron gets reduced, so this becomes two polyhedra then, but the sum of these two polyhedra has a smaller volume than the large one. Now, if we reduce it as much as possible, the hope is that this gives rise to a smaller search tree. And then in addition to these, let's say, bilinear considerations, we would also add what we call the shadow costs of this particular variable that come from the linear constraint. So this is a branching variable strategy that we have already available for regular MILP solves, these shadow costs, and these we just add on top of these two other criteria here for the bilinear branching. And now with spatial branching, so branching on continuous variables, there's a second thing that you need to consider. If you have a fractional integer variable, then the branching split is pretty clear. You just round down and you round up. But here, for the continuous variable, it's not so clear where you want to do this branching split. It's not always the best to branch directly on the solution value of this variable in the LP. It is actually better to go a little bit toward the midpoint of the current domain. And this is what we do, and this is also standard in the literature. So we pick a convex combination of the current LP value and the midpoint of the current domain. And then in addition, you need to be careful with numerics here. So you want to avoid branching on finite but very large values. So for example, you have an unbounded variable, then it is a very bad idea to say we split the domain at a point, let's say at 1 million or so, because then this 1 million would become a right-hand side of our LP solves, and this would then enter into the linear system solves, and that can turn out to be very bad. So, and then you also want to avoid tiny child domains if the LP variable is very close to a bound, so you want to move a little bit more to the midpoint of the interval then. And you, in the node selection, that's also important, you want to avoid very deep dives, which can happen with these continuous variable domains. Okay, let's see how these different things affect the performance of the overall non-convex solver. So again, the default setting, which is the branching strategy that I have just explained, is our reference, which has a value 1.0, of course. And then if we would not add those shadow costs that come from the linear constraints to the branching scores, so would not let them influence the variable selection, then we would lose 25% of performance. So this is really significant here. But then the other idea of looking at the volume of the McCormick polyhedra, if I disable this, then the solver gets actually like 14, 15, 16% faster. That was a surprise to me as well, so I thought this was a good idea, but apparently it was not. And then I looked a little bit further and found that if I just use it in a different way. So in the current version of Gurobi 9.0, I was using this particular McCormick volume reduction with a square root function and added that into the score. When I instead use the logarithm of the volume reduction, then I can actually get a performance improvement out of it. So if I do that, then we end up with a 0.82 performance number, which is like 18, 19, 20% about faster than the current default. And of course, this has already now been added to our master version. It will be the case now then in the next version of Gurobi. Okay, finally, let's come to cutting planes. So that is also very important to deal with those bilinear constraints. Of course, for general non-convex MIQCPs and also for non-convex mixed bilinear programs here, all MILP cutting planes apply. So you can always separate Gormley cuts and mixed integer rounding cuts, zero half cuts, what have you. All those are useful here as well, but there are a number of cutting planes that are very specific to bilinear constraints. And those are the, I would guess, most important ones here, the RLT, BQP, and PSD cuts. So RLT comes from the phrase reformulation linearization technique. This means you pick a linear constraint of your problem, multiply it with a single variable. So that means your constraint becomes quadratic, right? You have lots of quadratic terms now because you have multiplied it with a single variable. And then you look at these quadratic terms, and for some of them, you may have already such a Zij monomial variable, and then you can just replace it by this. So that's actually the goal of those RLT cuts. For others, where you don't have such a Zij variable, because this particular product did not appear in your original problem formulation, this you would just linearize, for example, with the McCormick relaxation. And then in the end, after doing all this linearization or substitution, you end up with another linear constraint. And that can actually be violated by the current LP solution, and this is your RLT cut. This is very powerful for those bilinear programs. One can actually also separate those for mixed integer linear programs, because such products for variables that include a binary variable can also be appearing in mixed integer linear programs. And this we can find and then separate RLT cuts for those as well. Okay, then BQP cuts. Those come from facets from the Boolean quadratic polytope, which is actually equivalent to the cut polytope. Currently, we have only implemented the very most simple ones of those this Boolean quadratic polytope, which are the triangle inequalities. So this is a special case of Padberg's clique cuts for the BQP. And then there are the PSD cuts, which come from a positive summative definite relaxation. So for an SDP relaxation of our problem. So here the idea is that you look at the PSD cone defined by this relation that the variables Zij should be equal to xi times xj. In matrix formulation, it means capital Z. The matrix is equal to x times x transpose. And if you then move the xx transpose to the left-hand side, you have z minus xx transpose is equal to 0, and then the relaxation is that z minus xx transpose is positive semi-definite. And for this PSD cone, you can then separate tangent cuts, and those are the PSD cuts. This has not yet been implemented in Gurobi, but we are currently looking into this, and this will probably make it into the next version. Okay, let's look finally at the performance of those cuts. So again, when you look at the default setting, which includes all of those cuts, except of course for the PSD cuts, which have not yet been implemented, then we have again this value 1.0 as reference. And now if I only disable the RLT cuts, then I lose already 37% of performance. And more importantly, if you look at the number of timeouts, so those are the models that this particular version cannot solve within the time limit of 10,000 seconds. Then this timeouts of 20 goes up to 110 without the RLT cut. So those are really, really important to be able to solve non-convex MIQCPs. Then if I do the same experiment with the BQP cuts, I don't see anything. So there are some path changes here, but overall, on average, the performance is really identical. Also, the number of timeouts doesn't change. So those BQP cuts seem to be not that useful. But if I turn off both, so RLT cuts and BQP cuts, then the performance really gets bad. We lose 75% of performance and introduce a large number of timeouts. What I get from these numbers is that I guess those BQP cuts are basically dominated by our RLT cut separation algorithm. So that means if you have already our RLT cuts, then you don't need the BQP cuts anymore. But if you don't have RLT cuts, then the BQP cuts would actually help. And then the final bar here is when I disable all the cuts. So that means you can see the small degradation from no RLT and BQP cuts to no cuts at all. This is very small degradation, so that seems that the other MILP type cuts, so Gurobi cuts, MIR cuts, and so forth, are not helping that much. But in terms of timeouts, it's increasing a bit more, so they do something at least. Okay, and with this, I'd like to transfer control to my colleague Eli Towle, who will now give you a presentation about the practice of those non-convex MIQCP solves.
Okay, thank you, Toby. So like Toby said, I'll be going through a small example of how we can solve something known as a pooling problem. I'm using the Gurobi Python API. And this is a special problem because it contains a non-convex quadratic constraint. So previous versions of Gurobi could handle convex quadratic constraints and objectives. So we'll be looking at an example of Gurobi 9.0 solving a problem with a non-convex quadratic constraint. So the important distinction here is that we're solving these problems to global optimality. If you were to give this problem to maybe a different nonlinear solver, a lot of these will just look for local minima, local solutions to the problem. So instead, we'll be using spatial branching, like Toby was talking about, to branch on these continuous variables and make sure that we're finding a global solution to the problem. So what we're going to do in this little Jupyter notebook is we'll introduce the pooling problem, we'll describe the mathematical formulation of the pooling problem, and then we will build and solve the problem using the Gurobi Python API. So what is the pooling problem? It's a problem that shows up in the petrochemical industry, and the idea is as follows. So we are given a set of source pools of crude oil, and each of these source pools we can use to extract crude oil from the earth, and each one contains a different percentage of sulfur. So sulfur is an impurity in oil, so a lower percentage of sulfur in the oil corresponds to a higher quality of oil. So in addition to these source pools, we also have any number of intermediate pools that we can use to blend together the source oils that we extracted from the source pools. So effectively, by blending these pools together in these intermediate pools, we are coming up with a whole new oil product that contains its own particular percentage of sulfur. And finally, we will have additionally some pools at the end that represent the products that we're going to sell, these new oil products. So we're going to construct these again by blending together maybe our source pools, maybe some of these intermediate pools together to create this new oil product. And these final products will have restrictions on them. So primarily, they have restrictions on the oil quality, meaning the sulfur percentage cannot exceed some specified amount, as well as the amount of product that we can actually produce. So we assume there's some demand for this product, some market demand, and it doesn't make sense for us to produce more of this product than we could actually sell on the market. So the example of the pooling problem we're going to look at today is from this 1978 paper by Haverly. Okay, so the first thing we'll do is import the Gurobi Pi package, and then we will define the data that's used in this small example in this 1978 Haverly paper. So the data definition I don't think is necessarily too interesting, but what is interesting is a visualization of the problem. So here we have a visual graph of the problem that we're looking at. So we'll go through this here. We see these rectangular nodes in our graph. So A, B, and C, these are going to be our source pools of oil. So they represent 3 different kinds of crude oil that we can extract from the earth. And each one of these source pools contains a different percentage of sulfur and costs a different amount per unit to extract. So for example, crude oil source A contains 3% sulfur and costs $6 per unit to extract. And as you can imagine, if the source oil is of higher quality, then it might cost more to extract. So in this case, crude oil source B contains only 1% sulfur, which is quite good, but it costs $16 per unit to extract. The arcs in this network will correspond to how we can move our oil from one pool to another. So we see this in the middle, we have this pool P, and this is going to be an intermediate pool. So it's not a source pool, it's not a product pool. It just represents an intermediate blending step that we're allowed to perform in this setup. So we will get oil into pool P by blending together some amount of oil from source A and some amount of oil from source B. After we've done that, then we're going to send oil into our output product pools. So products X and Y on the right here, these are these pentagonal shapes. And we create these products by blending together oil from intermediate pool P as well as from source pool C. So product X, we can sell at $9 per unit on the open market. And there are restrictions on the sulfur quality, like I mentioned earlier. So product X can contain no more than 2.5% sulfur, and we can sell no more than 100 units of product X. Additionally, product Y will sell for $15 per unit and can contain no more than 1.5% sulfur. And we can sell no more than 200 units of product Y. So the goal in this problem is to make as much money as possible. So we will, our money will be calculated, our revenue, or rather I should say our profit is calculated as our revenue less our costs. So we want to, our revenue comes from selling these output products, and the costs are calculated based on how much of each of the source pool oils we extract based on the unit extraction cost. So next we'll look at the mathematical formulation of this problem. So the key variables here, the 2 variables we have are these flow variables, Xij. And Xij represents the amount of flow that we're moving from one pool I to one pool J. These are the arcs in the network. Additionally, we have these quality variables, Yi, and there's a variable for every pool or node in our network. And this quality variable Yi represents the percentage of sulfur of the oil that we have at that particular pool. So let's go through the objective and constraints of this problem quickly. So our goal again is to maximize our profit. So our profit is calculated as our revenue less our costs. In this case, our revenue is calculated as the sum of all of the inbound flow, sum over all products of the inbound flows into that product multiplied by the corresponding unit selling price for that product. And our costs are calculated similarly as the sum over all of our source pools of the amount of outbound flow from these source pools multiplied by the corresponding unit extraction costs. So now on to the constraints. Let me make this a little bigger. Onto the constraints, we have first this flow balance constraint. The flow balance constraint, we only have one in this case because we have this constraint for each of our intermediate pools. So in this case, this constraint says that the sum of the flow inbound to intermediate pool P must be equal to the sum of the flow outbound from pool P. The next constraint is the tricky one in this problem. This is the constraint I've called define quality. So we need to somehow set these yi variables for each of our nodes in the network. So how do we calculate the sulfur quality, this yi variable for each of the nodes? Well, this is going to be the sum of the sulfur weighted inbound flows into the node divided by the total amount of inbound flow into this node. So we can write this constraint as follows. And it's tricky in this sense because we have all these bilinear terms. This is what Toby was talking about earlier. And it's additionally an equality constraint. So it's a non-convex quadratic equality constraint. And this is what makes this problem tricky, effectively. Next, we have constraints to fix the quality variables for each of the sources. So the sulfur percentage in sources A, B, and C is given a priori, so we don't need to make any calculations with these, so we just fix them to these values that were given. Next, we want to have a bound on the quality of the oil products that we produce. So this says that for product X, the sulfur percentage can not exceed 2.5%. Likewise, for product Y, the sulfur percentage cannot exceed 1.5%. And lastly, we have these maximum demand constraints, and this just says that we cannot sell more of a product than there is demand for. So in this case, the sum of the inbound flows into a particular product cannot exceed the demand for that product. So we will model this problem using Gurobi Pi. So the first thing we'll do is construct a define a function. So given some model n, we will do the following. So first we will add the flow variables to the model. We are adding these xij variables, one for every arc in the network or connection between our pools. Next, we define these quality variables. We'll add these to the problem. And we have a quality variable, a yi variable for every pool in our network. Next, we'll fix the quality for all of the sources. So this is, again, just saying that for crude oil sources A, B, and C, we know beforehand what the sulfur percentage is, and we'll just fix these yi variables to those values. And the last thing we're going to do is set an upper bound for the yi variables for each of our product pools. Next, we'll look at the objective function, or we'll define the objective function rather. So we create a Python function which will add the objective function to our model M. And again, the objective function is calculated as the total cost, the total revenue minus the total cost, which is our profit. And this is what we want to maximize. Python function we'll define here is the define constraints function, which is going to add all of the constraints to our model. So the first thing we'll do is add these balance constraints, these flow balance constraints. And recall that we had a flow balance constraint for each of our intermediate pools, which in this case was just one pool P. And these constraints say that the sum of the inbound flows into pool P must be equal to the sum of the outbound flows from pool P. Next, we'll add these demand constraints, which say that the sum of the inbound flows into a particular product cannot exceed the market demand for that product. And the last constraints are those tricky ones that contain these bilinear terms, which effectively set these quality variables, these yi variables, for each of our nodes or pools. So again, we calculate these yi variables to be the sum of the quality weighted inbound flows into a node divided by the total amount of flow into the node. Okay, so now we've defined these functions that will add all of the constraints and objectives and define the variables, and we can ask Gurobi to solve this problem. So first we'll construct a new model object. We'll add all of the variables, add the objective, add the constraints to the problem. The next thing we'll do is set this non-convex parameter equal to 2. And all this does is tells Gurobi that, yes, if the problem is non-convex and you can't figure out a nice way to linearize it, I still want you to solve it to global optimality using this spatial branching technique. And then we will optimize. So a couple things to note in the output here. First, we see that this is a continuous model that's non-convex, Gurobi says, so it's going to solve it as a MIP, and that just means that Gurobi will be branching on the continuous variables. And we see that the optimal solution, it allows us to make $400, which is maybe not great in the standard margins for oil companies, but in this case, I'm happy with it. So it'd be interesting to visualize the solution. So we can, like we did before, we can construct this, an image that shows what's going on in the solution here. So the optimal solution in this case is basically for us to produce only product Y, and we create product Y using a 50-50 mixture from crude oil source B and crude oil source C. So we'll take 100 units of each, mix them together to produce product Y. And as you can see, the resulting output product will contain 1.5% sulfur, which was the upper bound on the amount of sulfur that product Y could contain. Okay, we'll play around with the data just a little bit here to finish this demonstration. And the first thing we'll try is to increase the demand of product X from 100 units to 600 units. So currently in this problem, we're restricted in that we can only produce 100 units of product X. So maybe if we could produce more of this product, it would suddenly become more profitable for us. So we'll just change the demand of product X to 600 units and solve this problem again. And here's our new solution, which is very similar to the first, but in some sense reversed. So now instead of mixing one part oil B with 1 part oil C, we're producing a 50-50 mixture of crude oil source A and crude oil source C. And again, we'll produce as much of product X as we can, 600 units in this case, and the resulting mixture will contain 2.5% sulfur. So the last thing we'll do is see what happens if we change the price, the extraction cost for crude oil source B, which is currently set to $16. Let's see how the problem changes if we were to reduce this to $13. So maybe in this current setup, we're not extracting any oil from source B because it's prohibitively expensive. So again, Gurobi will solve this problem with non-convex constraints and give us the following solution, which says it is most profitable for us to produce, again, 600 units of product X, but this time using a mixture composed of 3 parts crude oil source A and 1 part crude oil source B. So that's the end of this demonstration of Gurobi 9.0 solving a small non-convex quadratic program. So now I'll turn it over to Yuri to handle our Q&A session.